Heather happens to be the dog mom of one of his best friends, so he gets very excited whenever he sees her. So I get the after-lunch crowd, which I know can be a little bit difficult. It's the last day, but I just ask for everyone to be as present as possible, and we'll get going. So in case you didn't read the agenda, the elephant in your data set, addressing bias in machine learning. Typically, this talk covers classical machine learning models and bias injection within them. I will cover a little bit of more modern-day applications as well. So, hello, my name is Michelle Frost. I consult doing responsible AI out of Accountable Intelligence. By day, I'm also a senior developer at a design and technology consultancy based in Kansas City, Missouri, called CREMA. And then I'm also a member of the Center for Practical Bioethics Ethical AI Council. And most importantly, Wilbur is the star of the show. I like to generally acknowledge him in that you can look at him for 12 seconds or so. Occasionally, my brain likes to reboot itself, and should it do that, he will come in and help me. So this is a lot to get through, and it's a bit of a heady topic. And it can be uncomfortable. So I'm going to start just by acknowledging that and a couple disclaimers. Often, we get to walk into a room and just be a technologist, just be a developer, just be a data scientist. But in this talk, you also have to be a human. So sometimes I like to shake things up a little bit. And if you're close enough, let's just take 20 seconds and be a human. And if you're next to someone that you haven't met before or you have met them, just give them a hello. And okay, so this is, again, a big topic, right? And it's honestly not what we can get through in an hour. So what we're going to do is basically a shallow but wide introduction. And what I hope to do is to just kind of give you an idea for the field of fairness and the things that we're looking at. And while we go through this talk, there's going to be some examples at each step. And these are real companies, and I don't bleep out the name of the company because, number one, instead of listening, then you all would be Googling saying, who did this? And number two, it's okay. These are big companies. Some of you have worked for them, maybe with them. We're all familiar with them. The point is that it can happen to everyone. And we need to be very aware of the problem, be aware of how the problem presents itself, so that we can take the steps to mitigate it. This is not to shame, this is to fix. And the biggest thing I'm going to stress here, and I'll say this multiple times throughout the next hour, this is not just a technical issue. This is a socio-technical issue. And what I mean by that is as engineers, as data scientists, as technologists, we can take a technical approach and we can mitigate it, but we're not going to solve it alone. And I won't get on my responsible AI tangents, but that does apply to the entire field. So what's our agenda? We're going to go through a little exercise, maybe make some people uncomfortable. That's okay. And then we're going to talk about bias. What is bias, right? What do we mean when we talk about it in a social context, in a human context, in a statistical context, in a machine learning context? When does it become harmful? And throughout this, I'm going to pair each of these with different examples of harmful bias. It's not always just what you think. It might not just be the data set. It could be different sampling methods, for example. And then we're going to talk about how do we measure and quantify it, okay? How do we translate this social problem into a mathematical and technical problem so that then we can start deriving approaches? And then how can we manage it, right? As, again, technologists individually, but as technologists collectively, and as humans as a group. So what's our goal today? I want everyone to be able to walk out of this room and feel empowered to be an active participant in discussions of bias in AI systems. So let's start with our exercise. Before I flip to this next slide, I'm going to give a couple caveats. These next little pieces are observed in the USA. So the context of this is going to differ across different cultures, across different countries. And I'm not going to ask anybody to raise your hand here, but a lot of times when we think of privilege, the first thing that might come to mind is skin color. And while that is a section here, there are many spaces of privilege that we can occupy. And privilege isn't meant to be a shame if you find yourself included in a space of power, in a category of privilege. But what we have to know is that if we hold power in a space, then we might have a blind spot. And if we have a blind spot because we don't understand someone else's perspective, then we might erroneously inject bias. And as a tangent, this is why it's so important to have diverse team members, and I mean diversity of all forms. So I'm going to read through these because it's hard to see. And in the center of the wheel, you hold the spaces of power. Again, US, so there might be contextually some differences. And on the outside is the marginalized groups. What I'm going to do is just read the category and then who holds the space of power. And as I iterate through these, I just kind of want you to maybe check off and say, ooh, is that something that I kind of sit within? Is that something that I didn't realize that I held power within? And so these categories, we will start with the blue at just about 12 o'clock. Skin color, white, neurodiversity, neurotypical, mental health, stable, physical ability, able-bodied, religion, Christian, wealth, rich, again, some of these are subjective, but age, adult, education, post-secondary, housing, homeowner, transportation, you can drive, political affiliation, again, US, Democrat, Republican, primarily ruled by a two-party class, marriage, homogenous, citizenship, citizen, employment, you're salaried, language and communication, you're a native English speaker, sexuality, heterosexual, monogamous, gender, cisgendered man, body size, slim and muscular. So again, we don't need to call ourselves out, or if you want to, feel free, but did this surprise anyone? Was there a space that maybe you hadn't thought of as holding a privilege in it? Okay. Before we move on, who is concerned about bias in AI and technology systems? Who doesn't think it's an issue and we're blowing it up? And that's okay. No one? I don't believe you. We're here to have a conversation. We're here to have an engagement, okay? This is a respectful place, and I'm going to open it up for dialogue at the end. And here's the thing. If we cannot have respectful conversation in this room, we're not going to have it out in the world. So we have to approach it together. And if we have differing views, that's okay. We can listen to each other as long as it's done respectfully. All right, let's get into it. What's bias? Yes, one giggle. All right, well, societal bias. Let's start with the big picture, okay? This is the frame. It's the bottom of the iceberg. Systemic bias. It's prejudices and stereotypes present within a society that influence behaviors, attitudes, and decisions. They're reflected in policies and social norms and cultural practices. Get down a little more individual, human bias. First thought, second thought. Has anyone heard of this? Yes, cool. So this is an idea that a lot of times the biases that we hold are biases that were influenced from our surroundings as we grew up, perhaps, maybe around family, around our communities. And sometimes the first thought that we have is developed by that. We're responsible for our second thought. So human bias encompasses a whole range of different individual judgment and decision-making. There's, I think, like 21 different categories of bias. Everything from confirmation bias, like, hey, every time I wear these socks, my favorite sport team wins. And so now you're biased towards wearing the socks. There's many different biases within this. Statistical bias, okay? What's that? Well, a systemic deviation of an estimator creates a bias from the true value of the parameter it estimates, right? And this can come from flaws in data collection process, and our sampling, and many different things, but basically it's part of an error, right? And I say part of, and we'll get into that. Okay, what about AI system bias? When we create systems that have systemic and unfair discrimination embedded into models and algorithms, this can result from skewed training data, from flawed design processes, and it can lead to unequal outcomes across different types of users. Now, let's drill in a little bit, because AI is a giant field, right? We encompass a lot of things. What about machine learning? Well, this is actually closer to statistical bias, but it's a systematic error that occurs in the model itself due to assumptions made in the machine learning model. So it can lead to models that consistently make predictions that are too simple. They don't capture the complexity of the data or the system that it's operating within. Now, I can't talk about harmful bias without talking about the necessary bias. Sometimes bias is necessary. Say you lose your keys, okay? You are guided by an assumption of where your keys might be. You're not going to go look in the fridge. Maybe you're going to go look in the fridge. You're likely not going to go look in the dog kennel, because it wouldn't make sense for the keys to have landed in the dog kennel, right? So in a machine learning model, it's a search process. And search is guided by a set of assumptions, otherwise we'd be searching blind. And this set of assumptions is referred to as inductive bias. And basically, so Tom Mitchell, 1997, the formal definition of inductive bias is the set of assumptions combined with the observed training examples that deductively entail subsequent instance classifications made by the learner. It's not always a bad thing. And in fact, sometimes we might want to tune bias towards a desired outcome, especially if we get it wrong in a certain way leads to a harmful type of error. Okay, I promise this is the last statistical slide for you. But we also have to talk about the bias variance trade-off, right? So we've all heard of the terms overfitting and underfitting. This is because of this trade-off between bias and variance. And we can actually formally define error as bias squared plus variance plus noise, which is irreducible error. Okay, we've gotten our statistical methods out of the way. Let's talk about harmful bias. Oh, I'm so sorry, Jody. So what about when it becomes harmful? So the following few slides, I'm going to use a wonderful paper called A Framework for Understanding Sources of Harm Throughout the Machine Learning Lifecycle. This is a 2021 paper by Suresh and Guttag. And what they did was basically, let's identify the spaces in an ML lifecycle where we can get it wrong and we can inject bias. So to kind of help me decide how deep we go here, how many of us are data scientists, machine learning engineers, and operate within this space on a pretty regular cadence within our job? Okay, let's go over it. So this top slide, it's a little hard to see, is our data generation, okay? So if we roughly divide the ML lifecycle process into two phases, right? We're looking at our data generation and then our model building and implementation. So we start on the top left-hand side with what? The world. We're looking for data, okay? And we go out and we find the data, and then we create a population selection, right? And then from that population, we have to measure it. What's our goal? What's our target? How do we define that from different attributes that we've created in this data set? And then we have our data set, okay? And then we have to pre-process it, right? We split it into training and testing subsets. And from there, we get to go into our model building and implementation. So we have a data set. It's been split. We have a problem. We have to define an objective, right? We have to optimize on that objective. We have to define our model. How do we define our model? Well, based on the objective. We have to evaluate it. How do we evaluate it? We use benchmarks. And then what happens with it? We say, oh, we've hit X amount of accuracy. Looks good enough to me. Ship it. It goes out into the world. And it has real-world implications. So the paper found 7 sources of harm in this life cycle process at each of these points. And we're going to go through these one by one, don't get me wrong, but we start with historical bias, we move into representation bias, measurement bias, and then within our building we have learning and aggregation bias. We evaluate it, we have evaluation bias, and we deploy it, deployment bias. And what happens? What happens when we release a model that is making predictions in real-world applications? They cycle back up into the data that we're pulling from. Okay, this is the easy one to start with. We've all heard of the phrase garbage in, garbage out, right? If you start with a crappy data set that has a bunch of garbage in it and bias, guess what you're going to end up with? So even if you perfectly measure the data set, even if you perfectly sample that, if the world as it is or as it was contains prejudice in the domain that you're looking at, you're going to have a data set that contains bias. Now, we can handle that, but we have to recognize it. We can kind of handle it. Caveat, this isn't a solved problem. Okay, an example. So this was an experiment on ChatGPT 3.5 by Dr. Hades Kotek and Dr. Ravit Dothan. If you do not follow them on LinkedIn, they are fabulous. They have been working in this field for a long time. But basically the premises of this is they were trying to get ChatGPT to admit that maybe the nurse was a male and maybe the doctor was female. And so they start with the sentence, the doctor yelled at the nurse because she was late. Who was late? According to the given sentence, the nurse was late. Okay, fine. She was late. Well, what if we start swapping around pronouns and nouns and try to make a sentence that structurally wouldn't make sense for the doctor to be male? It then starts trying to justify, well, you actually must have asked this question wrong, or this sentence doesn't make sense because it must be. And this is a fun thought experiment you can do across a variety of domains. You can say, tell me a story about an engineer. It's going to tell you a story about a man. You can say, tell me a story about an engineer named Michelle, and there will be something in the story about the gender construct in engineering. You can do the same thing. Tell me a story about a nurse who is male. It's always going to say, even though it's a woman-dominated field and his parents wanted him to become a doctor. And there's some funny ones in there, you know? It's like, what do Russians like to drink? Vodka. It'll always pair those together. But it's still a bias, right? Okay, what about representation bias? What if a sample underrepresents a part of a population? And this isn't always bad, but it can become problematic. When the target population does not reflect the use population, if the target population contains underrepresented groups, and if the sample method from the target population is limited or uneven. Who remembers this? I think this was 2015, if I'm not mistaken. Yeah, 2015. So, yeah. Android released this feature that starts automatically classifying your photos. And an engineer called out, like, hey, you've tagged me and my friends as gorillas. Why? Exactly. There wasn't enough training data, dark faces. Does anyone know how Google fixed this at the time? They removed gorillas as a label. The problem was too steep to fix it immediately, that the best solution was to remove the label itself. I've heard we've solved this since then, but I'll need a Google person to confirm that for me. Okay, what about measurement bias, right? So features and labels, they're a concrete measurement, right? A proxy to represent a construct, an idea, or a concept. What happens when we get it wrong? What happens when it's complex? If we're doing an image classification, we can all agree that this is a glass or a cup of water. We can get really detailed and argue about it, but it's pretty simple, right? It's straightforward. What about things like creditworthiness? What about ideas like recidivism? Well, as it happens, we're going to talk about recidivism today. So, has anyone heard of COMPAS? This is a system in the United States, and COMPAS stands for Correctional Offender Management Profiling for Alternative Sanctions. And the system was built in the late 90s, I think deployed in the early 2000s. At one point, it was being used by 47 out of 50 states. And it wasn't independently reviewed until 2017. Now, recidivism, to define, is the likelihood that a defendant or someone who commits a crime is going to go on to commit another crime, okay? But if we really want to start looking at recidivism as a construct, in the United States, we know that there is a big problem with policing. So is it truly an indicator that someone is going to go on to commit another crime, or is it an indicator of a much more complex social issue that involves policing, because different communities are policed at different rates? And when the system was reviewed by ProPublica in 2017, they released their findings, and they found that Black defendants were 2 times more likely to be classified as a false positive, meaning classified as likely to go on to commit a crime, and they did not. Meanwhile, white defendants were 2 times more likely to be classified as a false negative, meaning they were not going to go on to commit another crime. The system predicted that, and yet they did. And in ProPublica's documentation, there are several examples where it just doesn't quite make sense. Now, I have to admit that, or I will state that North Point rejected ProPublica's findings. North Point is, again, the creator of this system, and they said that ProPublica got it wrong and they didn't have enough data. So since then, this has been a hot topic in the fairness community, and I'm not going to give a percentage, but a large amount, greater than 50%, agrees with ProPublica's findings to the point that ProPublica's COMPAS dataset is one of the most widely used in fairness research. We're going to talk about this as we go, because this one actually checks every single box for our examples. Okay? Aggregation bias. This is an assumption that a one-size-fits-all model will map inputs to labels consistently across different subsets. What do we know from that wheel of privilege that was brought up earlier? That things mean different things across different contexts. If I say spill the tea in America, I'm going to lean in for some hot, juicy gossip. If I say it in England, someone might be offended. If we're building a text classification model to predict risky behavior, and I shot off a text that said, I'm going to be late, I'm on LSD. Red flag. She's making bad decisions. If I was in Chicago, I'd still made a bad decision, but I could also be on Lakeshore Drive, also referred to as LSD. Okay, well, what about healthcare? If we want to build a model that predicts diabetes, we have to understand that certain markers perform differently across different ethnicities. So if we don't take that context into account, we're going to build a model that performs differently across different subsets of people. Now, learning bias is probably one of the more complicated ones here because we have to make a choice, right, when we're modeling an objective. And certain objectives might prioritize one thing while diminishing another. And if we prioritize, for example, we want to minimize cross-entropy loss in a classification model, we might have a model that has more false positives. Maybe we want that. Maybe we don't. We have to understand that, though. Hard to find an example here because that would need an open source model, but we can make some guesses, right? So one thing we'll talk about is how accuracy can sometimes have another trade-off with fairness. Because when we're dealing with data that comes from an unfair world, if we want to increase fairness, it means we take a hit in accuracy. So if you blindly go and prioritize accuracy across different fields without accounting for that nuance, you're going to have a lack of fairness. This was another one that hit a bunch of headlines, and I think 2018, Amazon had created a hiring tool that just immediately was like, no women in tech. There's at least a few of us. Okay, how do we evaluate it? What happens if the benchmark itself is biased? What if the benchmark doesn't represent the use population, right? A model is optimized on training data, but the quality is measured against benchmarks. So if there's a benchmark out there that's been established as the high criteria, and we're all measuring up to it, we actually might have had a better model at some point, but we said it wasn't good enough because it's not meeting that benchmark. This was a study done a few years back that at the time was looking at the top 3 facial recognition APIs. So that was Microsoft's Face++ API and IBM. And overall, if you look at overall accuracy, it looks pretty good. But if you start digging into the types of errors across different skin tones and also between genders, you find a gap. And I'll also call out that a lot of these studies, still look at gender as a binary problem too, so that's a whole another range of the equation. But from this study, the largest difference was a 34.4% difference of error from IBM between a darker-skinned female and a light-skinned male. All right, we build our model, we're doing pretty good, right? It goes out into the world. What if we intended it to be used in a certain way, but yet it's being used in another? So, for example, Compass originally was supposed to help judges decide if they should set bail. How risky would it be if we allowed this defendant to meet bail? But some judges ended up using it as sentencing measures, okay? So it's, building a hook that was meant for a tuna fish and someone's out there catching sharks with it. It's a framing trap. Now, we can't necessarily mitigate how people use our products, but we can make sure that we're responsibly testing them and imagining all those different scenarios and trying our best to create guardrails. I have some book recs at the end. This is always going to be one of them. Virginia Eubank's Automating Inequality. She looks at 3 different case studies, and one of them was on a model that predicted child abuse. And what she found was that it performed really differently for lower class families. Why? Because protecting children looks different to different families based off of their means. How am I doing? 30 minutes? Okay. All right. Bias in generative systems. Again, this is still machine learning, but this is a lot of what we're interfacing with. So I will give you a couple examples. We're not going to go in too depth in here because that's a whole other talk. This was a really beautiful UI study. Actually, if you go to this webpage, the designers that worked on this project and the entire project itself was absolutely fabulous. It came out, I believe, last year from Bloomberg. And basically what they did was they said, give me a photograph of a X. Give me a photograph of a politician, of a CEO, of a criminal, of a terrorist, of a housekeeper, of a fast food worker. And then what they did was they started to just take out the features and look at the variation of skin tone and do a distribution on what types of skin tone came out from different requests. And what did they find? Surprise, surprise. Bias. Why? How are these models trained? The historical data. Feel free to shout out answers, guys. This is going to be a chat. Okay, another one I have to call out because I did get a comment once that said whoever built Gemini listened to the likes of her, which is kind of funny. Who saw this earlier this year? Yeah. Why? We didn't build in context, okay? We can't just have a model that says, hey, go do this thing, give me this thing, but don't actually have historical context or knowledge about it. Another segue for another time, but any sort of model that we're dealing with in the large language foundation model space really needs multiple and an adversarial network to create a chain of checks and balances. It's a talk for another day, but I will just leave that with there. Okay, so what are we going to do about it? Any ideas? You may not answer, Jody. Denny? Huh? Yeah. Yeah. Yeah, exactly. That'd be a great place to start, right? We should at least try and measure it. We should at least be thinking about this. So one question that I get quite frequently is, well, can't we just take out the protected attributes and then it's blind? We wish it was that easy. No, we can't, and this is a deep conversation, but the short answer is no, we cannot because of Simpson's paradox. It's not actually related to The Simpsons, but I giggled here. But basically, this is it's a statistical phenomenon that says when we collect data in such a space, these attributes are so tightly woven, it doesn't matter if we take out one because they bleed across the others. So even if we took out something like race or gender, enough things have happened in the social context of which we're collecting the data that we may as well actually have it there so that we can be aware of it and we can measure and mitigate against us. And I'll show that in a little bit here. Okay. Fairness. It's a field of machine learning research. And what are we trying to do in fairness? We're trying to manage and mitigate bias. No one cared about this for like a long time, and then all of a sudden everyone was like, oh shit, guys. This is a problem. And now fairness research is popping out so often, it's very frustrating to do literature reviews because there's a new paper coming out all the time, which I personally love. I love how many people are working in this space, and it's still not a solved issue. Why? Because there's no free lunch. because there's not going to be one solution that fixes all problems, because we have to understand the context in which we're operating so that we can create a meaningful solution towards it. So, what does it mean to build fair systems? Well, first off, I want to call out a few things. You hear a lot about, well, ethical AI was what we used to call it, and then it came out with the term responsible AI, right? Sometimes I mention the word ethics and I just see the eyes glaze over, and that's okay, that's a business conversation. But then I say, what about risk? Do you like lawsuits? We're driving towards the same goal. We might call it something differently, but we're trying to reach the same goal. So sometimes we do have to frame it differently as technologists when we're speaking to business people. But importantly here, equitable AI is a very specific idea that AI should benefit everyone fairly, and we should address issues like inclusion, accessibility, and fair distribution of advantages. I know there are some thoughts going on right now that should be addressed by a social scientist. I am here to give you the technical approach, but it's a complex system. We're not operating in vacuums here, right? Okay, so how are we going to measure it? Well, no one can agree on that either. Last I checked, there were, I think, 26 different measures of fairness, different mathematical measures. Why? Because, again, there's no free lunch. There's not a one-size-fits-all solution. But I'm going to introduce you to just a couple of concepts. So as you go forward, you can think of, what if I measured against this measurement? So one that we talk about often is statistical parity, also called demographic parity. Cynthia DeWerk is an amazing researcher in fairness, and she's come up with several of these measurements. So basically, this just ensures that individuals from different groups have the same probability of receiving a positive outcome. Why did I highlight that? Because it actually doesn't care about the ground truth. It just wants to know that we have an equal probability of predicting maybe genders to go on to receive a loan. That gets a little messy, right? Because we're actually not looking at the ground truth, and we're kind of throwing that out the window, but it still starts to give us a framework to understand how our system is operating in. Equal opportunity is very similar, except it really wants to know about qualified. It wants to say what in this data set would make a row, an entity, qualified to receive a positive outcome. And then how do we look at those qualified entities and then look at the protected classes within them and say, yeah, our probability is off between classes. So we start to kind of narrow it down a little bit, right? Okay, equalized odds. Well, this is a stricter path, and we basically require that the true positive rate and the false positive rate are roughly the same between different groups. So we can start looking at this in terms of ratios, which is what I'll pull up in my demo. And what we want to do is we want to get as close to 1 as possible, depending on how you're using a ratio. Predictive parity. Okay, we're starting to get into the ground truth, right? So this is basically that the predictive positive outcome has the same precision across different groups. Treatment equality, now we're focusing on balancing the ratio of false positive to false negative rates across different groups. Personally, I like to look at all of these so that we can understand the full problem, right? Because at data scientists, we don't just want one little window into the picture, we want to understand the entire environment. So if you were doing research on a system to measure bias, you might look at all these things, and it actually might even tell you more about your data, might tell you more about your model, and give you insights on how to even make your model better, because now we're starting to look at the different types of errors that we're producing. Now I'm going to start talking quickly because I have 19 minutes. All right, mitigation. So we're going to start with a technical approach. We can break this down into roughly 3 categories. There's active research going into each of these. So the first is kind of the easiest to visualize and understand. I'll do a quick demo that is in the pre-processing space. What do I mean by pre-processing? I mean that we're trying to mitigate bias before the data is trained for the model, before the model is trained on the data. Okay, so we want to look at our weights, right, at our sampling methods, at different transformations that we can do prior. Now, in processing is techniques that modify the actual learning mechanisms or the algorithm to incorporate constraints and objectives directly during the model training itself. My personal opinion is that this is where the solution should lie. Okay, we want the model to recognize these things. We can manually do things, but if we could create models that recognize bias themselves, we might even get deeper insights into systems in our society that generate bias. A lot of work is being done right now also in the multi-objective optimization space. So I spoke earlier about that trade-off between fairness and accuracy. Well, how do we take these 2 objectives and seek an optimal solution that finds a midpoint without damaging one or the other? How close can we get to a compromise between these 2? And if we can solve for that, then that also is a better conversation to a stakeholder when I say, hey, I'm going to take a 4% hit on accuracy for a 2% increase in fairness. They don't always like that, but if you can explain that we're finding the best solution between the 2, it tells a better story. And then post-processing, I don't love this one. So basically, we take the results from our model, and then we manipulate the outputs or predictions. So for an example, that compass that we'll look at, they give a decile score. And I've seen some research where the decile score is between 1 and 10, 1 being very unlikely to go on to commit recidivism, 10 being highly likely. And it understood that there, in post-processing techniques, that it operates, not in a vacuum, so they'll try and alleviate scores of protected groups. But that's not very scientific, is it? We're still making guesses. And then we can measure it, but... So for me, personal opinions here, stating that, in processing is where we should be aiming for. But pre-processing is still a good place to start. Oh no, live demos, okay. So, let's see if I can. They moved my things around. And she's very tiny. You can see it? Okay, we're going to go through this kind of quickly. And I will also disclose that I decided to change my demo and my bias very recently. So some of this is messy, but we get to dig in together. And also, I found out a very unfortunate thing. This is a new computer, and usually I demo this on a fairness dashboard that is contained in the Microsoft's RAI widgets package. And it breaks on several new things. First off, it doesn't play nicely with newer versions of Python, and there's also a break on Homebrew. So to all my Microsoft friends out there, please fix it for me. So what are we looking at here? If we scroll down, this is the data set that ProPublica put together on Compass. So I think there's about 7,000... going up here, 7,214 entries in the main data set from ProPublica. And it looks at things like name, first name, last name, the screening date, the sex, the date of birth, what types of attributes were related to the crime itself. And then they did a 2-year study that said, okay, this is what the system predicted. 2 years later, what has happened? Now, my caveat here about this demo is that this data set is not meant to be predictive. It's meant for analysis so that we can look at how the system performs. So what I am going to do here after I show you their analysis and some pieces from it is we're going to try and make a model, a logistic regression model, to replicate the compass system as close as we can as possible, which is not great. It's like 76%. That's fine. And then from there, we're going to look at different sampling methods to build that model and how those ratios are affected. So if we just take a rough glance down through some of these, so we pre-process. So here's the distribution of race. Now, I dropped out everything except for the African American and Caucasian defendants. Why? Because they have the highest spread. But also this was what the ProPublica research was looking at. So we start off with unequal groups, right? And then we can start looking at a distribution of score by race. So orange, if you can't read, is the white defendants, and the blue bars are the black defendants. And the black defendants are actually fairly equal, right, across the distribution. The white defendants have a huge spike on the low end. We can also look at the priors count. So for 0 priors count, the higher distribution on the low end is actually held by black defendants. And then we can also look at the average scores by race and gender. And I think, oh, I've got some more. Okay, so then the actual and predicted recidivism rates. So on the orange bar, so on the left side, we have our black defendants. On the right side, we have our white defendants. The blue bar is the ground truth from ProPublica's study. This was what the 2-year recidivism positive, yes, we went on. Orange was the system predicted. See some differences there, right? So, in the sake of time here, gotta zoom in again. So we're gonna look at just a couple things on pre-processing, or methods to mitigate here. Okay, so before we get into modeling, this is if we're looking at the ratio of the compass system itself as provided by ProPublica, okay? So we are using the, that predicted recidivism from the system, which when we model, we use that as our target column because we're trying to match the system. And then we use the 2-year recidivism as the ground truth. And our results are exactly what ProPublica reports, that black defendants are about 2 times more likely to receive a false positive rate. So on this top data frame up here, that's our top entry. And then whites, so they have the 0.23 ratio. And then on the false negative rate, the second column, we can see it's flipped. White defendants are about 2 times more likely to receive a false negative rate. Now we can also look at this in ratio, and the ratio I took was if we look at from white defendants to black defendants. So meaning that a result that is greater than 1 indicates how much the rate is higher for white defendants than for black defendants. And if the result is less than 1, this is how much higher the rate is for black defendants. There are smoother ways of doing this, but in the interest of just kind of giving you guys the ratio, I wish that I could pull up the RAI dashboard because it's beautiful and visualizes these bars for you, but alas, we have to look at numbers. Okay, so then let's go ahead and model it. We did a very simple logistic regression for the ease and explainability of this. But this is, so again, I think we're able to achieve like 76% accuracy. The ratio looks different, but we're still pretty close to the spread. We still have about 2 times more for white defendants on false negative rate, about 2 times more for black defendants on false positive rate. Okay, well, what about that Simpson's paradox? What if our model is blind? So we drop out race before we train, and our results are interestingly almost the same as the original compass system. Okay. What if we balance the groups? What if we have the same number of entities in the white defendant group versus the black defendant group? What does that do? She got kind of worse. Why? Because it doesn't matter how equal the groups are if their targets are unequal. In fact, if we're blindly sampling, just, give me this percentage of black defendants to match the smaller group of white defendants that we have, we're probably missing really important entities because we're not evening our spread. So if we're going to go through this, we have to understand we can make it worse if we don't know what we're doing. So what we want to do is balance the target ratio. We're almost the same there. Now, accuracy of the system took a little bit of a hit, but we were able to increase fairness, and that was just from a couple lines of code. The problem is that means our data set has just gotten a lot smaller because we have had to ensure that we have the same negative and positive outcomes across both groups. And while this is fine for a demo, that might not operate well in real life when we need as much data as possible to build our systems. But it goes to prove a point that the way that you sample and you collect your data does in fact make a difference. And screen mirroring off. Well, smoother than it was sometimes, so small wins. All right, I said this was it was a socio-technical problem, right? We walked through a technical approach, but it's a socio-technical problem that needs a socio-technical approach. What do I mean? I mean a lot of things, but three of the most important. We need multi-stakeholders, okay? We need diverse groups and individuals that have a vested interest in the development, deployment, and impact of our systems. We need a human in the loop. These machines can't make these decisions on their own for human-related problems. We need to measure the risk of the application, the risk of the decisions. And when the risk is high, we need humans involved still. And of course, human-centered design approach. So this is an ongoing and iterative design process that prioritizes the needs, experiences, and well-beings of the users and people impacted by the system. NIST has a wonderful framework for this. If it's something that you're curious about, you can search NIST bias management or human-centered design processes, and they have different frameworks that are really helpful to take back to your team and say, hey, what if we designed like this? What sort of learnings can we take away and can we incorporate into our design processes? Managing. Talk about governance, right? That's a whole other talk, but we need to move away from reactive governance and towards proactive governance. What do I mean? A lot of times when governance gets involved in AI systems, it's when it's too late. It's when there's been a problem. It's when there's been a lawsuit. Instead, we need to start in governance. And we need to have structured processes. We need SOPs. We need continuous monitoring and evaluation. We don't know how much bias is in our system unless we're trying to measure and evaluate it, right? We have to start there. We have to have somebody that tells us, you can take time to do this. You can bake it into your process. We need feedback channels. We need anonymous ways for users and for team members to feel safe enough to say, hey, I think there might be a problem here. And in our process management, how do we bake in time? Now, we all kind of giggle because, like, we're devs, right? And we know even trying to get time for tech debt is hard. What about ethical debt? So it starts with education. Again, for the last time, this is a socio-technical issue, okay? And on the note on ethical debt, oftentimes, depending on your corporation's structure, it can be really hard to make waves at an individual level. You can go out and get all the education that you want in the topic, but if someone above does not prioritize the time that you're asking for to build in these checks and balances, it's going to get stuck in the pipeline. So it truly does need to come from a top-down approach and a top-down appreciation for the problem. And again, if the eyes glaze over on ethics, personal tip, talk about risk management. If anyone wants to take a photo of this slide, I've got a lot of books that I love, but these are some of my favorites right now. I just finished this, The Worlds I See, and it was absolutely fabulous. Does anyone know who Dr. Lee is? She was one of the original data scientists that put together ImageNet. So she's absolutely fabulous, and this is kind of her life story paired with her understanding the need for responsible AI. So I'll give that one little shout out. Also, Biased is a great place to start. It's actually not really a technical book. It's more of a social book. Just kind of gets you thinking about spaces that maybe you haven't had a chance to think of before. And now a note from our sponsors. So I work for Crema. We're a design and technology consultancy. We do everything from design sprints to full product builds. If you'd like to get in touch with someone from our sales team, that is our QR code. And then also, I'm a member of the Center for Practical Bioethics. We're taking a 3-tiered approach to implementing ethical systems within healthcare organizations and hospitals. So we look at process improvement tools, education and training, and then executive level support. And if you'd like to reach us, it's a QR code, do a lot of different trainings, evaluations, procurement, and connecting with consultancies that can do the work. And if you'd like to get in touch with me, that's my LinkedIn. And I only saved you a minute and a half for question, comments, or cheap shots. Denny?
How do we, so we know that a lot of the big AI models and the big AI companies are American-based, US-based. How do we handle cultural differences, so things that are perfectly normal or not okay in the States, but the opposite at other parts of the world?
Yeah.
That's my biggest thing the last months.
Yeah, and I wish I had an answer for you. I don't. It's kind of funny, too, because if you look at even regulation and policy, it differs a lot, right? It differs across borders, and yet technology does not have borders. So how do we handle that? And that's a governance question. But the best thing we can do is digging into it, right? Raising problems. There have been, so I think yesterday it was actually, one of the Stable Fusion models got removed from Hugging Face, and it was the model that had a lot of CSAM, child sexual abuse material, contained within it. Why? Because enough people were like, hey guys, can someone remove this? And it was a big enough issue that there's now 404 on Hugging Face if you try and search for that model. So I do believe that there is a lot of community-driven efforts. And these are the conversations in the field that we have to be having. And we can talk about it over a drink later. Any others? I think there's time for one short question. No? Well, I will leave with one parting thought. we talked about that trade-off, right, between accuracy and fairness, okay? This is an active decision, okay? It's the equivalent for taking a harder right over an easier wrong. And we are accountable for it as individuals, as companies, as entities, as communities. And so if there's anything that I'd like you to take away from this, it's that each one of us has a call to this problem, to educating others, and to working on it. And thank you, guys. Oh, you're fine.